Hello, this talk is about the Quantum Communications Hub. I'm going to give an overview of our activities, but the way I've laid out the talk is I'll begin with an introduction to quantum technologies and what they are briefly. Then I'll talk about the UK national programme very briefly, so you can see where the Quantum Communication Hub sits within that. And then I'll say a little about what the Hub has achieved over the last 5 years of our work, but the main focus of this talk is then to give a forward look on the things that we plan to do over the next 5 years. Okay, so new quantum technologies. So the whole idea behind quantum technologies is that these technologies enable us to do something either better than we can with conventional technology, or something that we can't do with conventional technology. And they utilize one or more of the fundamental features of quantum physics to do that. So that's the principle of superposition, or the phenomenon of entanglement, or the fact that when you measure things in quantum physics, you generally disturb them. So these fundamental aspects of quantum physics are what play center stage in new technologies and underpin their capabilities. And so the first one I'd like to mention very briefly is quantum computing. And so the idea that you have superposition, if you can put a quantum machine in a superposition of very many states and let it evolve, then in principle you can calculate very many things in parallel at the same time. And if you do something clever at the end with those very many quantum amplitudes, you can generally find out something interesting much more quickly than you can do through doing those computations by conventional means. So quantum computing has applications in simulation, in modeling, in cryptanalysis, we'll come back to that one, database search, and various other applications. At the minute, there's a whole load of candidates being investigated worldwide about what quantum computers would be constructed from: trapped ions or atoms, semiconductor devices, in particular superconducting devices. We know Google and IBM are both working on that direction. And then there are other solid state applications which also involve use of light in order to do quantum processing. So that's quantum computing, based on parallel computing with very many quantum amplitudes. The next quantum technology is to do with sensing and imaging, and rather flippantly, if you take two quantum systems that are entangled with each other and bounce one of them off some object and then recombine these two things, you can in principle learn more about that object than you may be able to do by using the same resources in just conventional states. And entangled states are one example. You can use other various non-classical states of stuff as well. And for quantum imaging and sensing, what do people use? Well, certainly they use light, but also you can use atoms or nanomechanical devices. So you might use light for imaging, you might use atoms for sensing gravity or other fields, and you might use some nanomechanical device in some kind of non-classical state to also sense external fields of some sort. And one current example of the application of non-classical states is the upgrade to the gravitational wave detector LIGO, because they're now employing squeeze states of light in order to better sense gravitational waves than they could with conventional coherent states of light in their interferometer. So that's one practical example that's being put in place now. The main relevant application and technology for this talk today is quantum communications. And in quantum communications, the idea is that Alice, who is always the transmitter, if Alice sends quantum states over to Bob and somebody tries to have a look at these quantum states in transit, then in general, their peaking will impose some kind of disturbance on those states. And Alice and Bob will be able to infer that someone has been eavesdropping. Now, in the quantum technology application that's communication, we essentially always use light as the carrier, some form of light. This might be sent down an optical fiber, it might be sent through free space. Both of those are ways to perform quantum communications, and I'll mention both of them later. But essentially, we always use quantum states of light. And if someone tries to intercept that light and measure it in transit, then you can infer that that eavesdropping has gone on, which means that you can work out when someone is trying to intercept your communications. So that's a very brief overview of the space of different quantum technologies. Now, if we go back, well, actually, one thing I'd like to say before we progress to the wider UK program, just to give you a bit of context, then in particular, because we're interested in quantum communications, secure quantum communications, it's interesting to look at the impact of other quantum technologies, because it is already known that if people could build very substantial quantum computers, large quantum computers, then we could break current public key infrastructure, which is based on RSA or elliptic curves or other mathematical techniques all in this family. There was an algorithm invented by Peter Shaw in the mid-1990s, Shaw's algorithm, that shows that if you had a sizable quantum computer, you can invert the hard mathematical problems which underpin our current public key infrastructure, and you can break it. And you may think that's just a threat in the future, but Michele Mosca from the University of Waterloo has long championed that we should think more carefully about that, because if the data that you're transferring around at the minute securely has, let's say, a shelf life, how long you'd like to keep it secure, and if you know how long it would take you to completely re-implement your secure communication system, then if the sum of those two times is actually greater than the time you think it'll take for people to realize a big quantum computer capable of breaking RSA, then you should be worried right now, not in the future. So quantum computing, as well as all its very positive benefits, also has the potential threat, if you like, to break current crypto. So that's one aspect, quantum computing. In addition, I've very briefly mentioned that new quantum sensors and imaging will be able to take us beyond what we can do with current limits. But the good news is that despite both of those threats, if you like, from other quantum technologies, we do know that there is a way of doing secure quantum communications, key sharing, and I will come back to that in a bit more detail. So we do know that there is a way that we will be able to do secure quantum communications in the future, even when big quantum computers and all manner of quantum sensors and images exist. So that's one good aspect. We know how to do secure quantum communications. In addition to that, people are now working on new mathematical cryptography, so-called post-quantum cryptography or quantum-resistant cryptography, which goes beyond the RSA and elliptic curve stuff that we know is vulnerable to quantum computer attack and should be resistant to future quantum computer attacks. So there's actually a process being run by NIST in the USA at the minute, and actually it's just moved to stage 3 of selection of new candidates for PQC. So we've got two ways going forward. We've got secure quantum communications and we've got post-quantum cryptography. And I think the majority view now is that future secure communication systems will combine both of these two aspects. They will give us the optimum quantum safety in the future, that's being safe against attack from other quantum technologies. So that's the context of all the quantum technologies. I'm now going to move on and say a little bit about the UK national programme, just to position the Quantum Communications Hub, and then we'll talk about what the hub is doing. So in December 2013, after quite a lot of campaigning and the UK government listening, they found a substantial set of new money, which came, if you like, directly from the Chancellor, George Osborne, who was then the Chancellor of the coalition government. And he produced £270 million as an initial start for a new UK national quantum technologies program. And that took about a year to put in place. And so the program started towards the end of 2014. And its phase 1, which ran for 5 years, finished towards the end of 2019. And a second phase has now started. So in phase 1, there was this money was used for a variety of activities. And the centerpiece in terms of technology development was 4 quantum technology hubs that were set up. And I'll say what a hub means and what they look like in just a minute. But there were 4 technology hubs established to cover the whole space of quantum technologies. There were centres for doctoral training. There was, in the beginning, a modest Innovate UK programme for industry-led projects. And actually, towards the end of phase 1, this was expanded hugely with an injection of significant more money. And there is now a quantum theme within the Industrial Strategy Challenge Fund programme that is run through Innovate UK. And so this funds all manner of new technologies, but there is now a quantum thread in that for big industry-led projects. And so that's a good way forward for industry getting involved. There was also investment in the National Physical Laboratory and skills and training, and so on. And so with the additional industry money that was added to the 270 million, and then with a renewal of the programme for the following 5 years, so that started late last year and it will run to the end of 2024, so that's phase 2. If you add up all the phase 2 contributions, including the industry ones and all of the government money, then the estimate now is that the whole programme over a 10-year period is going to be worth close to £1 billion. So this is a very substantial investment by the UK. And there are other investments of similar or even larger size elsewhere in the world, notably in China and the US. Okay, so that's the UK national programme. As I said, it funded 4 hubs, 4 technology hubs, and those were chosen to cover pretty much the space of all quantum technologies. And I've given here the 4 hubs, and I've given them their names going forward as in phase 2. And so the hub that's focused on sensors using atoms and timing based on atomic clocks, that's led by the University of Birmingham. So that's the technology hub in sensors and timing, led out of Birmingham. The sister one, if you like, that focuses on imaging as opposed to sensing is led by the University of Glasgow, and that mainly uses light for doing all sorts of clever quantum imaging. The Quantum Computing Hub in phase 2 is called the Quantum Computing Simulation Hub. That's led by the University of Oxford. In phase 1, they very much focus strongly on ion trapping and connecting ion traps by photonics. In phase 2, they have expanded now to include other different platforms, including superconducting qubits and various other solid state approaches. There is also now, I haven't put it on the slide, but there is also now in phase 2 going to be a UK National Quantum Computing Centre. And so this is going to be a physically located centre on the Harwell site just south of Oxford. And if you like, that is almost the technology transfer route for this quantum computing and simulation hub. So they've been able to throw their net a bit wider in terms of what they investigate in phase 2, because they have a transfer route into the National Quantum Computing Centre. So that leaves the final hub, which is the one that I lead from the University of York. And what we do is we focus on quantum communications. You'll see that most of what we do is focused on quantum key distribution. I'll say a bit more about that shortly. But we are looking at all manner of quantum communications. And so those are the 4 hubs that cover the spectrum. This is literally a cut and paste from the proposal that we wrote for phase 1. So it's very important to understand that these hubs, they're big distributed collaborative bodies, and I'll show you all of our partners in just a minute. But it's important to note that the hubs are focused on technology development, not basic science. So what we were tasked to do when we put in our hub proposals is that we were told we needed to put in proposals to develop new technologies. So Basic quantum science has been funded over very many years in the UK through the Engineering and Physical Sciences Research Council and other funding bodies. But the investment that's gone into basic quantum science over many decades, we were supposed to take that and build on it and show how that could be turned into working technology. So we weren't submitting research proposals, we were submitting technology development proposals. And the way we did that over the first 5 years, the ones that have just gone, is most of what we did was based on quantum key distribution. And the reason for that was that quantum key distribution was already understood from a theoretical perspective, but also it was already implemented and you could buy certain technologies even. So what we wanted to do was to take what was already there for QKD and advance that in different new directions and get those commercial ready. And most of what we did over the last 5 years focused on that. We did do a bit of exploration into new approaches and things that go beyond QKD. We had one activity in phase 1 working on that. You'll see we have a few more in phase 2, as I will explain. Our budget in phase 1 was 24 million, and we got an extra 2 million capital to extend the quantum network that I'll tell you about shortly. So we got almost a tenth of that initial 270 million pound investment, which sounds a lot of money, but when you spread it over very many partners, actually you need income from other places, and our experimental work has leveraged very strongly off our partners having other research income. So quantum key distribution, as I said, most of what we've done in phase 1 and most of what we will be doing actually in phase 2 is based on QKD. And I'm not going to explain the protocol in detail, but what I will do is explain one or two of the principles and I'll make one or two important points. So the idea is that if Alice sends quantum light signals to Bob, lots of them, and Bob measures, then there is a protocol. There are in fact quite a number of different protocols that they can use in order to take the data that they have after they've done this transmission and measurement. They can take that data and from it they can distill a secure key, and what that is a string of random digits that only they know. And the promise from quantum physics that Alice and Bob get is that they are the only people who know this string of random digits. And if they have that string of random digits, they can use it in various ways. But the first important point to note is that it is the establishment of that key between Alice and Bob that is the quantum part. That needs quantum physics, it needs quantum measurements, it needs quantum transmission from Alice. Once the key has been shared out between Alice and Bob, they can use it for what they want. So the use of the key is not quantum. So they can use it to secure communications, encrypt some sort of data. They could use it as a rolling PIN number in financial transactions. They can use it over the internet. They could use it to get in through secure doors. They could, in principle, use it as a rolling password. There's all sorts of applications. The applications are not quantum. So once Alice and Bob have shared the data, they can use it for what they want. Almost all of these uses, in fact, probably all of these uses, rely on their security or their functionality for the key being a consumable. So basically, you use it once and then you delete it. And you don't just throw it away, you make sure you delete it so others don't find out what it is. But it's a use once thing, a key. And because of that, it needs replenishment. And if it's going to be replenished, that's back up to here. And so that's again a quantum process. So the key distribution and the key replenishment are the quantum parts. The use of the keys is classical. That involves conventional data. So that's QKD. I said I would share with you our hub partners, and here they are for both phases 1 and phase 2. So don't think of a hub as a localized thing in the UK based at one university or one institution. It's a big spread out collaboration of roughly 10 universities and very many companies who play different roles as part of the hub. And so you'll find that every single hub, each one of the four, has a slide like this showing all of their partners. So all four of the hubs are big spread out collaborations across the UK. Now, in phase one, as I said, most of what we did was based on QKD, although we did one or two other things as well. And so here is a very brief overview of what we achieved in the first 5 years. And so, as I said, the brief of the hub that we gave ourselves is that we wanted to take QKD and push it in new directions and push those towards commercialization. And so one of the things we did is we focused on short range free space, so-called consumer QKD. And you can think of consumer QKD as having Alice sitting in your phone and Bob sitting in some device in the wall somewhere. And you can establish key between your handheld device and the machine in the wall, which might belong to your bank or your employer or the government or the health service or whatever. So you could share keys with these various entities, and then you could use those keys for subsequent transactions of various forms. So we developed short range free space handheld, if you like, consumer QKD. That was one of the three directions that we took QKD. We also investigated chip-based communications, because in the end, you would like both the Alice transmitter and the Bob receiver to be small optical chips that could integrate into conventional electronics and be part of technologies of all manners. So you might have them installed in your computer and so on. And we clearly had success there because our partner, the University of Bristol, during phase one, produced the world's first chip-to-chip QKD demonstration. And also out of Bristol, there's been the emergence of a startup, KETS, which is focused on commercializing various aspects of chip-based quantum optical technologies. And so that's another direction that we took QKD. The third one that we did was established a UK quantum network. And I'll come back, we've got a bigger map of this in just a minute. But basically, there's a network around Bristol and one around Cambridge. And we're using parts of the National Dark Fiber facility to connect those two networks together. So we built, and we're now operating, the UK's first quantum network. So those were the three QKD based activities in phase one. In addition to that, we looked at some technologies that go beyond just key distribution, so quantum signatures and novel approaches to QKD, so-called measurement device independent QKD. And this activity, as you'll see a bit later, is extending into phase two. So those were our technology development aspects in phase one. I stress that I showed you the picture of all our industrial partners. We had very key and important partnerships with very many companies, but I've noted just a few here that particularly worked with us on the UK quantum network. But it's also notable that, and I mentioned earlier, Industrial Strategy Challenge Fund is run through Innovate UK. They fund big industry-led projects, and some of those are now up and running. And out of the first four that started, first four big ISCF projects, two of them were focused on quantum communications. And they've leveraged heavily off hub work, and they include numerous hub partners. So there's Aquasec that's led by Toshiba, and 3QN that's led by Arcit. So our phase one work has fed into both of these ISCF projects. So if you like, ISCF projects are one of our tech transfer routes. We could from a hub transfer technology directly into a company, but we could also transfer it to an ISCF project. And there will now be, over the coming months, many more ISCF projects starting up. And there will be further of those that are leveraged off our hub work to date. So ISCF, that's very important to us as a way forward with tech transfer. We contributed significantly through hub partners, NPL and Toshiba in particular, to standards work, and we'll be continuing that in phase two. So particularly through ETSI, So I know the ENETSI stands for the European Telecommunications Standards Institute, but actually it has worldwide membership. There are people involved from all over the world, and so standards are very important for new technologies, and we will be continuing building on our standards work from phase one. Another interesting aspect of the hubs is that they have money, if you like, that at the start of the hub program is unassigned. And so in phase one, we had roughly £4 million that we were told not to assign at day one, because there would be things that we would likely want to work on that we didn't know yet we wanted to work on. And it would enable us to be strategic. And we certainly were going forward with our, so within our phase one partnership resource, we used that money in particular to fund new ideas that were not part of the main hub proposal at day one, to fund new ideas, bring in new partners. And we used those in a strategic way with the idea that if there was a phase two, which we were optimistic about, we would be able to bring in some of that work that was developed through partnership resource projects in phase one and bring it into the main hub in phase two. And that's exactly what happened. And there are various, you'll see that we're doing significant work in phase two on quantum communications in space. Well, there was none of that in phase one. And we've expanded our work significantly on random numbers. I'll say a bit more about that. And there are other new protocols that we brought in during phase two. In addition to that, we introduced the Quantum Ambassador Scheme, which has set up A-level quantum education, so people can access in schools particular educational resources for learning about quantum technologies as part of that. And we're hoping to continue that into phase two as well. Okay, so that's a quick overview of what we've achieved in the last 5 years. I now want to have a forward look about what we're going to be doing in the next 5. So here's the quick overview, and then I'll talk about each of these points in more detail. So the big idea, if you like, that captures everything that we're trying to do in phase two is that we're aiming to look at integrated secure quantum communications at all distance scales. And so that means very short range, like the handheld stuff I've just mentioned, to the very longest distances. And the way we're going about doing that is we're leveraging, obviously, very heavily off what we've done in phase one. We're bringing in the new partners that we need to deliver in the new areas that we're introducing. And so in phase one, we had 4 parallel activities going on. In phase two, that's been expanded to 8 parallel technology activities, if you like. And then we have 3 that cross-cut and are relevant for many of the 8. And so I'm going to say a little bit about each of the 8 activities specifically, and then each of these 3 cross-cutting activities. So we'll certainly be continuing work on the UK quantum network in phase two. We'll be looking at 2 particular aspects of QKD and actually beyond QKD with entanglement, but these were not mainstream parts of the phase one hub, but they were also developed somewhat through partnership resource. So we're going to be looking at continuous variable QKD and entanglement-based networking, not just QKD. We're going to be continuing the handheld work for consumer QKD, and we're going to be, this is the big new one, if you like, that leveraged off some partnership resource studies we did in phase one. But in phase one, we had no long distance free space communications. We knew that was a gap, but we couldn't cover everything in phase one. And so in phase two, we're going to be looking at QKD in space. So we're going to have a transmitter up on a small satellite and a ground-based receiver. We're going to be continuing our work on chip-based technologies. And the nice thing there is because KETS now exists and there's now an ISCF project that's looking at commercializing some of these technologies, we can focus on the lower TRL concepts for chip-based stuff. So this is new QKD approaches being put on chip. We'll have a continuing activity in phase two on new protocols. we'll build on what we've already done, but we'll be introducing some new ideas as well. Again, some of those are fed in from partnership resource. Another one notable addition for phase 2 that we didn't really have in phase 1 is detector and source development. So during phase 1, we basically said we would take what we could get off the shelf and we would use it. So whatever detectors and sources we could get our hands on, we would employ those in our QKD and other technologies. With the changing world environment and the fact that some companies may no longer be supplying particular detectors, we were encouraged and we were very keen to introduce in phase 2 a specific work theme on detector and source development. So this goes wider than just our hub. In fact, detectors and sources for light are clearly important to Quantique as well. But we've got a program in our hub developing the specific detectors and sources that are relevant for us. But there's mirrored work in other hubs looking at the detectors and sources that they need. And so this, if you like, will feed into various other of these activities. So those are the 8 parallel themes that we've got going. Then we've got work continuing on standards and metrology and benchmarking of QKD and our other hardware. We'll be looking at putting together, I mentioned that the QKD and PQC together are probably the way forward for ultimate quantum safe, secure communication systems. And we'll be looking at integrating these two together. And we'll also be looking at clearly security analysis, testing and hacking to make sure that the systems really are secure. So that's the 8 parallel activities plus the 3 cross-cutting ones. And I've got a couple of slides now on each of these. So I'll just go through these one by one. So UK Quantum Network, well, as I said, we've already established it and built it. And what we want to do is we now want to develop it further. We want to explore it and see how flexible and dynamic it can be. We want to add things to it, and we want to combine quantum and conventional communications in as seamless a way as possible. Very importantly, also though, we want to use it as a demonstrator. So we want to engage with companies and other external potential end users, and we want to demonstrate applications actually working out in the real world on the network. And so that's going to be the basis of our activity in phase 2. What I should say is that for all of these phase 2 slides, what we've tried to do is we've tried to include the logos of the relevant university partners at the bottom. It would have been a bit of a squeeze to put in all the industry partners as well. So what we've done is we've highlighted the academic partners at the bottom of each slide who will be leading the work in this work package. And so you'll find that holds throughout the rest of this slide set. So the main ones here are the universities of Bristol and Cambridge, and we're contributing from York as well. So here's a bigger map of the UK Quantum Network. So there is a small network that goes around the city of Cambridge with 4 nodes in it. That Cambridge network actually links off to, and this is what we got extra phase 1 capital funding for. There is a network, and it's shown here more accurately with 3 trusted nodes that exist between Cambridge and British Telecom's Adastral Park research lab. So this is BT's main research environment here at Adastral Park near Ipswich, and we now have a working connection between Cambridge and BT. Then we're using bits of the National Dark Fibre facility to connect between Cambridge and Bristol, and there is also a Bristol network within the city of Bristol, and that's laid out in this kind of format. So the UK Quantum Network at the minute consists of Cambridge and Bristol interconnected, and then a link to British Telecom as well. And this network relies on basically two sets of commercial equipment. So we have We have Toshiba equipment that operates around Cambridge, and between Cambridge and Bristol, we have ID Quantique equipment that operates around Bristol, and we have ID Quantique equipment that operates between Cambridge and BT. So we're using industrial, commercial QKD equipment that comes boxed up to establish this network. And as you'll see, we hope to connect various hub technologies on top of that. So here's a kind of sketch of there are basically 4 different directions that we want to take the network in phase 2. This dotted box here indicates where we are at the minute with the current state of the UK quantum, the UK quantum network. And what we want to do is we want to take that in various different directions. We want to add new different media to it, if you like. So eventually we would like to connect it both to our short range QKD and the longer distance space QKD. We'd like to connect those into the network. We would also, as I've already noted, like to combine QKD with conventional communications and with post-quantum crypto to give the ultimate quantum safe, secure networking. We also want to go in multi-party directions, so we want to actually service multiple users rather than just one Alice and one Bob. And perhaps the most important direction that we want to pursue in terms of engaging external users is to look at new applications. So we want to see what secure quantum communications can actually deliver in terms of applications that would be useful in the real world to end users. And so we will be engaging with end users on various demonstrations. So that's basically the 4 directions in which we want to take the UK quantum network activities in phase 2. Okay, the next of the 8 parallel themes is CV QKD, so-called continuous variable QKD. This relies on continuous states of light rather than using single photons or pseudo single photon states as quantum bits to establish a key. You actually use continuous states of light, still quantum states of light, and you still need to measure them down at the quantum limit. But instead of single photons, we use continuous states of light. And there's a way of encoding quantum information into continuous variable states. The detection methods are different. You use homodyne detection rather than single photon counting. But there's merits to using continuous variables rather than just single photons. And our activity, as I said, it was built on partnership resource activity in phase 1, but we're going to leverage off the theoretical expertise that exists at the University of York to pursue various theoretical activities for CVQKD. But we also now have an experimental activity at York where we're building CVQKD systems of various sorts, and we'll be working with Cambridge to actually field test some of these on the UK quantum network. So just to give you a few examples, I'm not going to talk through all of these, but I'll just highlight 1 or 2. So we're interested in I mentioned very briefly earlier, measurement device independent QKD, and I'll say a little about the idea of MDI because it's actually relevant for not just for CV, but for ordinary QKD as well, and we'll come back to a little later. But the idea with MDI QKD is that Alice and Bob can send stuff to measurement apparatus in the middle, and if that measurement apparatus is set up suitably, then Alice and Bob can end up with stuff that they can use to distill a key. So they can get a shared key by sending stuff into the middle and by it being measured. Now, the nice thing about it is that, and the reason it's called measurement device independent QKD, is that you can actually let even the eavesdropper have the measurement apparatus. So the eavesdropper could deny service by just taking whatever Alice and Bob send and throwing it away. But what can't happen is that the eavesdropper can make Alice and Bob think they have a secure key when the eavesdropper knows something about it. So that can't happen in MDI QKD. So by doing this measurement in the middle, you don't care who runs that measurement apparatus, and indeed it could even be up on a satellite, or you could be using a satellite to distribute stuff down. You don't have to trust what goes on in the middle. So that's the nice idea, that you can do stuff where things happen in the middle, and you don't have to trust what happens. There are tests you can do, and if those tests are passed, then you can establish keys. So we want to do that kind of approach with continuous variables. We also want to consider using squeeze states. So in a squeeze state, even if you take the vacuum of the electromagnetic field, normally that vacuum is symmetric in the phase space, but you can actually squeeze it. So there's a fundamental uncertainty. It's not just a point, it's actually a fuzzy blob. And you can squeeze the uncertainty in one direction at the expense of expanding the uncertainty in the other. And those are so-called squeeze states of light. And in fact, I mentioned earlier that people were using squeeze states for improving the gravitational wave detection, because you can see in the one direction where you squeeze, there's actually lower noise than there was in the original vacuum, which is just a circle. And so on that basis, if you only use that quadrature, you end up with lower noise. And so we want to explore using squeeze states for QKD. We'll be doing it through fiber, but also we're interested in doing it through free space, transmitter and receiver, and that's clearly of interest for ground to satellite communications. And there are other clever things you can do, like two-way QKD, where actually Bob sends something to Alice. All Alice does is a manipulation on what Bob sends and sends it back, and you can generate a key that way as well. So there's a whole range of technology directions that we want to investigate with CVQKD. The third of the parallel work packages is looking at entanglement-based networking. So this goes beyond just key distribution, but it involves, so you certainly can use entanglement for key distribution. So this picture here from the University of Bristol, if you like, shows the whole of the evolution of secure quantum communications, from the very beginnings, just simple two-party QKD between Alice and Bob, all the way to what people call the quantum internet, where you have multiple nodes all interconnected, and they can share quantum level signals between each other. So anyone could do teleportation with anyone else or whatever. So we've clearly progressed beyond just QKD, and we're somewhere down in the middle, I guess, now. But we want to continue this progression towards the ultimate quantum internet. And this involves certainly the next steps, sharing out quantum entanglement. So entanglement you can generate in various ways. You can either do it through parametric down conversion, or possibly from quantum dot radiation in sequence. But you can generate pairs of entangled photons, and we want to investigate sharing these out over various network configurations. So it's already been done with a modest number of users. Entanglement can be shared out between multiple users already, but what we want to do in the future is to actually do it with rather more users and over highly connected networks. And we want to demonstrate that at least one of those users can be at the other end of a piece of real fiber on the UK quantum network. So we want to do many more users and change the network mesh, and we want to do it in a practical way as well, to show it works on the UK network. And there are various approaches that one can use to networking things together. There are various topologies for laying out networks, and those are going to be investigated, because another factor in how you might lay your networks out is if you've got superconducting detectors to do some of the detection of the photons, then it might be convenient to put those in only certain nodes rather than all of them. And so the network topology may also depend partially on the physical constraints of the technology that's being used. So that's one of the threads of our entanglement-based networking. So this is University of Bristol work. Heriot Watt are also going to be looking at related work on entanglement distribution, and in fact sharing out keys over multiple users, so quantum conference key agreement. That's again already been achieved within the hub with 4 users. So this is the, as I said, Harriet Watt work, but the idea is to extend that to be able to share entanglement over a number of users, and to do it over various network topologies and over networks that you don't trust. And so sharing our entanglement is a big theme of this particular hub work package. But also, in principle, we want to look at the first steps towards all optical quantum repeaters. So if you want to get to the ultimate quantum internet, where everything can be connected to everything else in a quantum way, then you're going to need to be able to ferry entanglement on and on from node to node, and quantum repeaters are what enable that. And almost certainly, in the end, you will also need quantum memory employed in that. So at the minute, both repeaters and memory are at the basic research level, but we want to push forward with that work and bring it as far to technology as we can. The third aspect, and this is led from the University of Sheffield, is to look at some theoretical aspects of entanglement-based networking, because, as I said, you can use entanglement distributed for key distribution, but you can also use it for other things as well. So if you can share entanglement out over multiple users, you can improve various quantum protocols. If you like, you can do distributed quantum processing, or at least take the first steps towards distributed quantum processing. And you can also do distributed quantum imaging or quantum data collection. And so there's various protocols that can be studied that go beyond just simple two-party key distribution utilizing entanglement. So we'll be investigating those. The next work package is a continuation of one of the phase 1 activities. So this is the free space consumer QKD, the short range phone to larger device activity. In phase 1, we had working devices. I mean, the target is that the end user Alice transmitter that goes in the phone has to be very cheap. It has to be small, compact, low power, and so on. But it has to be essentially negligible cost compared to the price of the phone hardware in the first place. You don't need huge performance. If you want to be able to exchange and top up a level of key in a second or two, then you don't need that much data for key exchange. So we're only targeting modest performance in order to get the device size right down. But what we want to do in phase 2 is actually integrate handheld, genuine handheld performance through having beam steering. And if you like, the quantum communications part is coming from the University of Bristol, and the beam steering and integration of that is coming from the University of Oxford. So this leveraged off partnership resource in phase 1 to bring in Oxford to do this. So in the end, we want to integrate the handheld performance to include beam steering, and we want to demonstrate this on a node in the network. So here's a picture of the sort of credit card sized transmitter section that would fit into a phone type profile. The idea is that this will get redesigned in phase 2, and it will be integrated with the pointing and tracking, so that you can have quite a wide field of view and movement. So it could be genuinely handheld. At the minute, the device sits in a cradle, and in the future, the aim is that it will function genuinely handheld. Another aspect of this work package is to think about in-room architectures, how things would go. So we were interested in the idea of having a quantum terminal, if you like, based on the ceiling of a room, and you could have very many user terminals sitting here that could all talk to this one in the roof through free space transmission over a few meters. And what we want to do to demonstrate that would be feasible is to go to a demonstration of fiber into free space, back into fiber QKD, and can that be integrated alongside conventional Wi-Fi in order to set up secure communication. So So the idea is that we want to be able to do secure comms in a room, if you like, to a number of terminals. So that's all of the short range stuff. One of the big new additions in phase 2, if I've mentioned already, is we're going into space. So I said our grand vision, if you like, for phase 2 was quantum comms at all length scales. And the way it works out is that because of excuse me, because of convenience, at the very shortest distances, handheld free space QKD is the most flexible way to go. In terms of moderate distances around cities and between cities, then clearly optical fiber is the way to go, because we already have a very extensive integrated optical fiber communications network across the UK and indeed any other country. So clearly we need to do QKD and quantum comms over fiber at those kinds of distances. But then if you want to get from continent to continent or from one side of the world to the other, then you're going to need to use ground to satellite to ground connections. That's the only way to really get from continent to continent. So free space at both ends of the length scales and fiber in the middle is the way to go. And so in phase 1, we focused on 2 of the 3, but in phase 2, we're bringing in the third one, which is the long distance free space satellite to ground communications. And our activity here is really broken into 3 stages. First of all, we want to develop stuff that is capable of going in a satellite. Then we want to test it and make sure that it works. And then we want to stick it up in a satellite and have a ground station that talks to it. So that very flippantly is the 3-stage approach that we're going to adopt. We've got various candidates for the sources. So the idea is that we're going to put a source on a satellite and have the receiver on the ground. We've got 3 candidate source directions, and it's not clear yet whether we'll be able to put just one or multiple sources up on a satellite. But we're going to investigate as candidate sources 3 different approaches. If you like, there's the standard so-called weak pulse or pseudo single photon sources, which is just a little light source. It's been filtered right down, so the pulses it emits contain on average about 1/10 of a photon or something like that. So these look like single photons. So this is standard weak pulse source that's going to be developed, and this is clearly also the kind of thing that we're already using in other work packages such as the handheld stuff. We're also going to be looking at an entangled source candidate, and I'll come back to that in WP8. And I've also already mentioned CVQKD in WP2, and we're going to look at developing a suitable CV source to put up in space as well. So we've got multiple candidates for stage 1, if you like, to develop these payloads. And then we'll see if they stand up to the potential conditions that they're going to encounter in space. On the ground, we basically need a receiver, and that receiver is, I suppose, the fundamental unit of the receiver is some kind of telescope that's going to catch the light. But then after it's caught the light, we then need a suitable quantum receiver. So this would be a Harmadine type detector receiver for CVQKD, or some kind of single photon counting device for entangled or single photon QKD source up on the satellite. So we're going to develop various sources to go with their partner, various receivers to go with their partner sources. And then we're going to have a telescope that will catch the light and route it into the receiver. Where we position that receiver is in the UK is still to be decided. We do have access to small portable ground stations. Bristol have one, and we have one at the University of York as well. So we may be able to use these for testing to determine the best site to place the large receiver. And so the large one's going to be a 70-centimeter telescope, so this sort of size. And so the idea is that, as I say, we'll put whatever receiver we need on the bottom of this to be compatible with the source that is transmitting from the satellite. And then the final part of this is that, of course, we have a satellite, and that satellite clearly has to have all the usual support and communication stuff on that a little satellite needs. But in addition, there will be a box where we can put a quantum source or quantum sources. And at the minute, the thinking is that this might be a 12U satellite. 1U is roughly 10 centimeters cubed, so 12 would be 2 by 2 by 3 centimeters, so about 20 by 20 by 30 centimeters. So not very big. They're quite small, these satellites, but you can get quite a lot in, and we're hoping to get at least, well, hopefully 2 sources in potentially. We can leverage very heavily. So in phase 2, we did some initial investigations in phase 1 under partnership resource, but in phase 2, we brought in expertise from the Rutherford and Appleton Laboratories space folk. So they're now a partner in phase 2. The good thing is that they are also the UK lead on a joint UK-Singapore CubeSat mission that is being planned at the minute. And so they're providing the satellite for that. And so we can basically clone that satellite design and then put in the hub quantum technology into that satellite in order to accelerate our satellite development program. And so that's the idea, in-orbit demonstration, where we put a quantum source up on the satellite and we have a suitable quantum receiver on the ground. I said we were going to continue our chip work, and I also said that, of course, now there's ISCF projects that are going to be utilizing chip-based optical quantum technologies, but in addition, there are now companies doing this. So that frees up the hub to target the low TRL interesting problems that are still outstanding, and that's good because it means we have the flexibility to pursue a number of parallel activities, and it's also going to link up into other work packages and chip-based activities. So some of the examples of the things we're going to look at are, for example, floodlight QKD. So floodlight QKD, I think, was invented by Jeff Shapiro's group at MIT, but floodlight is what it says. You actually send many photons per quantum signal that go, but those photons are spread out over different optical transmission paths, so that in any one of the modes there's rather less than one photon. So any one intercepting is still going to disturb in the same way that you get caught in usual QKD. So it's quite a neat idea to have high brightness photons and send them down many different paths, and integrating that into silicon photonics is something that would be very nice to pursue. I'll come back to it when we talk about cross work package activities, but we're certainly going to be looking at hacking and whether the optical chips that are produced are secure. And I mentioned already the nice idea of MDI QKD, where you measure in the middle and you don't have to worry about who owns the measurement apparatus. Well, we want to have that embedded on chip and then test it over the Bristol network. And so there are various aspects of QKD that we want to pursue, which I would say are low TRL for our chip-based activity. But another important activity, which is led by Cambridge, is the idea of low-loss switching. So in future flexible dynamical networks, we're clearly going to have to want to route quantum signals where we want them to go, even without measuring them. So for that, you need fast, low-loss switches, and that's being pursued by the University of Cambridge. It's crucial when you send quantum signals through networks that they don't pass through classical amplifiers, conventional amplifiers, otherwise those will destroy the quantum signals. So we have to be able to route quantum signals and switch them to where we want. And the idea is to produce switches that can do that for us. So that's our chip-based activity. As I said, in phase 1, we had activity on protocols that go beyond QKD, and we're going to continue that in this work package in phase 2, and there are 3 directions that we've got for starters, but we're going to open those up into others that come along. And if you like, this work package is theory driven, but the idea is that these theoretical ideas or new protocols will then feed into implementations that will work either in the laboratory or then over the UK quantum network. And so one of these directions is the idea of secure quantum tokens. This comes out of work by Adrian Kent at the University of Cambridge. And the idea here is, I suppose it's combining ideas from relativity as well as quantum information. So Adrian was the inventor a while back of the relativistic bit commitment scheme. So the idea that you can't influence things outside your future light code. And so if you put things outside the light code, then you can't influence them or get at them. And so that can be used, that forward-going light code, and also clearly you can't be influenced by anything outside your past light code. And so combining those things also with quantum with quantum information gives you flexibility for new protocols. And so this one on tokens enables you to identify a token at a particular point in the future. That's the only point where it's valid. And so that is it's, if you like, bringing a spatial element into the key distribution, and the fact that you can't signal faster than the speed of light. And so that's one direction that we're going in, new protocol beyond QKD. Another one which we've started, but we're going to work more on, is investigation of randomness. And so one nice promise from a genuinely quantum random number generator is, because it's quantum, if it generates a string of random numbers, if you have another identical quantum random number generator which you set up in the same way, it will produce a random string, and both of those random strings should pass any randomness test if they're good as random strings, but they should also have no correlation between them. And that's the promise you get from quantum physics, that a random string produced from one QRNG would have no overlap with a random string produced by another. So that uniqueness is very appealing, particularly for cryptography applications of randomness. But of course, in order to make that guarantee, you have to be very clear that the randomness that you're using to give the random string is genuinely quantum, and not just a mixture of quantum and classical randomness, if you like. And so in order to verify that, there are nice future ideas relating to NDI, QKD and so on, where you can again have measurement device independent randomness, which is very nice. Then the verification, if you like, that the randomness is quantum becomes a bit more straightforward. But at the minute, those are not so practical. And so it's important with current quantum random number generators to be able to quantify their quantum randomness. And so this is work led by Roger Kolbeck at the University of York, in collaboration then with NPL and others for implementing and testing this. If you take an ordinary quantum random number generator at the minute, you need a physical model of it, and then you have to verify what you get from experiment against that physical model in order to, if you like, certify or at least assure that the device is behaving in a quantum way. Then you need to make sure that you extract just the quantum randomness, and so that the random bit string that you end up is based only on the random quantum element of your device and not other random aspects of it. Obviously, it also has to pass the statistical tests in order to be useful randomness, but the key thing is being able to assure that what you extract is quantum randomness. So that's random number generation. So in phase 1, actually, we did significant progress, if you like, on quantum signatures, and this was mainly led by Erica Anderson at Heriot Watt and her collaborators. But at the start of phase 1, quantum signatures were a rather clunky thing in the lab, and then the protocol was developed so that you can actually now do signatures with just ordinary QKD boxes and a bit of a change to the post-processing and what you do afterwards. And so now quantum signatures have gone out of the laboratory and have been performed across networks in various places in the world. And so we want to continue work on signatures, but we also want to look at going beyond just, if you like, straightforward quantum communications and looking at quantum computation from a distributed and multi-party aspect. So that's 3 new directions of quantum protocols, but we will look at others as new ideas emerge as well. The final parallel activity, the 8th work package in phase 2 is, if you like, the component work. And as I said, we didn't really do any of this in phase 1, but with the changing world situation, we think it is very useful, and we were strongly encouraged to have an activity in phase 2 where we build both sources and detectors that are relevant for quantum communications. And so we're going to be looking at various forms of detector, and the superconducting detector work is led by Robert Hadfield at Glasgow, and the fabrication is done in Glasgow as well. And the idea is that if you have a tiny superconducting wire and you put it at just the right temperature, then when a single photon hits it, it will send that normal, and you will get a pulse that detects that single photon arriving. And so not only do we want to progress the development of the actual superconducting detectors, but we would also like to progress the development of the cryogenic system. So at the minute, obviously superconductors have to sit in a fridge, and if you could make a very nice, small, compact fridge, then it would be much easier to deploy superconducting detectors much more widely than they are used at the minute. And there's also the possibility of going not just to telecom infrared, but actually to mid-infrared and doing superconducting detection there. So there may be interesting applications for long-distance free space quantum communications in the mid-infrared rather than just telecom infrared or visible. So that's superconducting detectors. We're going to be pursuing those. In terms of a source, I did mention that we'd be looking at a candidate entangled source to put up on a satellite. This is work led out of Harriet Watt and Alessandro Federici. I think I may get it wrong, but I think even back when he was a PhD student in Austria, was one of those who worked on the original idea of an entangled photon source, which will be going up on the Singapore satellite, but is also already up on the Chinese satellite. So a compact single photon source through down conversion is something we're going to look to build as a candidate to put up on our satellite. So that's going to be work led out of Harriet Watt. An alternative source, it would be very nice if you had triggerable genuine single photon sources at telecom wavelengths. So that's the goal of the work led out of Sheffield by Maurice Skolnick. What we'd really like is we'd like a fast triggerable single photon source that works at telecom wavelengths, and the way we're looking to get that is by embedding a little quantum dot in the middle of a photonic crystal cavity. And so when you give the quantum dot a kick and excite it, it will then de-excite and spit out a photon at the desirable wavelength into the cavity. Now, if you want that de-excitation rate, if you like, to be enhanced by the Purcell effect, then you need the cavity Q to be good, and you need the cavity volume to be small in order to get this enhancement. And the good news is this has already been done at non-telecom wavelengths at 900 nanometers. And so the idea is that you'll grow quantum dots and you'll stick them in a cavity, and then the cavity will couple into a waveguide, and then you'll get the photon out into a fiber. So that's the idea. We want to build a bright single photon source at telecom wavelengths by embedding a quantum dot in the cavity. And the final WPA activity is led by Harriet Watt, but the fabrication will be done at Glasgow. And this is on semiconductor detectors as opposed to superconducting detectors. And so one appealing way forward for semiconductor detectors is if you can do nice germanium on silicon detectors, because if you can put germanium on silicon instead of other semiconductor approaches, then clearly germanium on silicon, you'd like to think would be more straightforward to integrate into conventional silicon electronics. And so the idea is to build semiconductor detectors based on germanium and putting them here into silicon circuitry. So it would be nice in the end. So I did mention that we'd done the first chip-to-chip QKD experiment. Bristol did that demonstration. In fact, the detectors in the Bob unit were off-chip. So the chip at the Bob end was for the analysis, but it didn't have the detectors integrated in. So one outstanding problem that would be nice to solve would be to have detectors that can be easily integrated into the chips that are being built. And so the idea is to come up with a suitable detector that will be easily integrable. Okay, so that's all of the 8 activities that we're doing in parallel. There are now 1 or 2 cross-cutting themes that I want to mention before I finish. The first one of these is a continuation from phase 1. So we want to continue our work on standards and doing the appropriate measurements to verify that the quantum communication technologies really do what they say they do. And so obviously the UK's National Measurement Lab, the National Physical Laboratory, is clearly the right institution to be leading this activity. And so NPL will be continuing their work on measuring various hub quantum technologies which are installed on the quantum network and also contributing to standards, mainly through ETSI, but it's interesting to note that various other standards bodies worldwide are now taking interest in quantum technology standards. So I think ETSI have kind of paved the way for this, and so we'll be continuing our contribution to standards. Okay, so this slide shows in a little more detail what NPL will be doing. They'll be looking at measuring both the transmitter and receiver units that we've got installed on the UK quantum network, but they'll also be looking at side channels and the countermeasures that can be taken against those. So side channels are where you have a difference between what is assumed about the technology in a security proof and what is actually true about the technology that's in the laboratory. If there's a difference between those two, then people can try and exploit that side channel to get around the QKD security proof. And so if you understand that and you can measure what the limitations are, then you can devise countermeasures to counteract the eavesdropping that might be exploiting a particular side channel. And indeed, there are standards being developed on this. So the idea is that as well as just looking at the transmitters and receivers that we've got, we'll be looking at various possible attacks that can be done against either the source or the receiver. Here, if you like, is a flow diagram for the way NPL would follow through on developing security assurance of a particular technology or a device. And so there is a tried and tested approach to, if you like, in the end, giving an assurance that a piece of technology, in this case, quantum communications technology, is actually doing what it says. Another cross-cutting activity is integrating together post-quantum cryptography and QKD. So I mentioned this early on as being highly desirable, and for this in phase 2, Queen's University Belfast have come on as one of our partners, along with the University of Kent, for looking at security assessment. In terms of integrating PQC with QKD, one very appealing way forward, particularly for the handheld scenario. So in the handheld scenario, you've got very many Alices and rather fewer Bobs. And in order for that to be a flexible and dynamic system, you want any Alice that has never met a certain Bob to be able to bootstrap from scratch a QKD exchange to share key. And so using a new PQC form of public key in order to authenticate an Alice to a Bob that she's never met would be a very interesting application. And so our first, I think, area for investigation of integrating PQC with QKD will be in the handheld scenario, but then we want to extend that out and undertake it in other QKD applications as well. But certainly, I mentioned earlier that there is a NIST process ongoing to select the new PQC candidates, and that's just moved to phase 3. And so we will now know which of the appropriate public key PQC candidates we should be pursuing with the integration. In terms of security assessment, it's important to not just test the individual items, but to test the whole system. And so it's going to be important to test the systems end to end, if you like, and we'll have both the University of Kent and Queen's University Belfast involved in that, along with NPL for doing the appropriate measurements. Something else we want to look at in more detail is hacking. We want to make sure that every single side channel gets picked up and looked at, and so that's quite important to do, even in the case where we've combined quantum and classical together. If we then have a combined system, we have to test the security of that combined system, not just the individual pieces. And we'll also be working on making sure that the quantum randomness that is provided by QRNGs is secure in the sense that it's not vulnerable to attack, and if you like, it's robust against external influences. So that covers all of our hub's efforts. Just to show you that this technology really is getting out there, this is a bit of free advertising for one of our industrial partners, ID Quantique, but just a couple of months ago it was announced that you'll soon be able to buy the latest Samsung Galaxy phone, actually with a quantum random number generator chipset embedded in it. So you really will be able to have quantum randomness in your pocket soon. So that covers the whole of the activity of the phase 2 hub. I've just left a few links here that you can follow up on. In particular, if you want to look at what we achieved in phase 1, you may well want to follow the link to all of the hub resources that are on our website. This gives you the URL of the whole UK National Quantum Technologies Programme, so it will link to the other hubs as well as ours. If you want, you can follow us on Twitter, and this is probably still worth a read. It's the most recent government report on quantum technologies, so a number of us worked with the government chief scientist of the time, Mark Walport, a few years back to come up with a Blackett review on, so this is on the whole of quantum technologies, again, not just quantum communications, but it was basically a statement of the government position on the various quantum technologies at the time, and it made various recommendations that we're now in the process of implementing. So that, I think, covers everything I want to cover. Thank you very much.